So last time we talked about the low Reynolds things, and things got really nice. I totally messed up the integration around the sphere. That was a disaster. I apologize, but I just got to push ahead on this one. So I think in the notes I do the integration better for that solution of like the drag force on a sphere. I didn't even get to really talk about how fundamental that is, but really like you can bound it, right? Inscribed sphere, outside sphere. Really want to get that across with low Reynolds flow. So you can just do so much approximation, and all due to that linearity of the governing equations. Okay, and then cooler part about that whole lecture was really just that sort of conceptualizing this, calculating around them for all types of different flows puts you in a different realm, and you can do it. So it's a good way to example on that. So, but what I did show is that we live in high Reynolds, right? Right, we live at this issue of a high Reynolds going on. You just look at our length scales and things like that. High Reynolds could mean a lot of things. There's this thing of ideal flow, which we talked about, which is potential analysis. Okay, so I don't mean that even actually, right? Because what do potential flows mean? Well, a potential flow was that the solution of this, it was the gradient of some scalar field. And this is, right, equivalent to this idea that, well, I'm assuming that the velocity field has no curl to it. It's irrotational. There's no mixture of the dimensions happening in the velocity field. And that is the assumption of ideal flow, right? It's a pretty stringent assumption. Very stringent, I'd say. So we're not even in that situation in most of our lives, I'd say, because it's not easy, right? Because this is a very small set of solutions. All of the velocity fields, it's all Navier-Stokes equations that have no curl. So it works for like wings and things like that, but we're not even on there, right? So what we do have in our life, I would say, in normal life, is, right? That is fairly true for us, unless you're using hypersonics or you're on a plane. But that's sort of, the plane lives in its own mechanical world. But you yourself don't really live there. You're not going to ever really experience that. You're certainly not going to experience the forces that happen on there. The outside of the plane is. You won't. You die. Or G-forces. You could do it that way as well. But we do have this. We do have this with us. We are usually low than Mach 1. Remember, go back to, like, really we really are sort of less than this. And if you go back to the first lecture, if you non-dimensionalize all the equations, it's really this condition. It's really that condition which lets you say incompressible. So in our life, we are incompressible. That's usually held. These are really equivalent statements. Okay, so this one we do get. This one not so much. So that pushes us into the issue of turbulence. Okay, so maybe to summarize where turbulence is, I have this nice little thing going on, right? So you have to think of things, at all stages of these equations, right? I have some Reynolds number scale for any type of flow scenario happening, right? So there is this Stokes flow world, right? Right, and this is that, in the Stokes flow where we went over a whole last lecture, where this is that sort of, you're really sort of going, right, going to zero. You have linear equations, and all the nonlinearity dies out. So this is a linear theory, which is very important. Okay, the other thing, there's another part sort of on this scale, and that you could say sort of moderate. Maybe you could even say, around 1. So maybe 1 sort of lives like, certainly in here, so I'll put 1 here, and this is 0. A lot of the relationships we had for Stokes flow even still work. That drag on a sphere that equation, the 6 pi, and that wonderful, nice relationship, it's actually like within 10% still if your Reynolds number is 1. Reynolds number being 1 is a pretty slow velocity. So, they're kind of, these are still sort of creeping next to each other in the theory at least. Okay, so this one, one way we could think of this as well is we could think of, this moderate being, at least for how we're handling it, this idea that like the square root of the Reynolds is at least much bigger than 1. And this puts you into that asymptotic theory. Okay, so right here, this is really asymptotic theory. Okay, that's where all the asymptotic relationships are going because you expand in like these powers of Reynolds. I mean, really all of these things would work there, but there's something that breaks down even for that, and it's a really awful breaking down that ends up happening. There's on this sort of really bad one, really on this outside, things totally change. Okay, and this is sort of when, this is this issue of when this gets much less than 1. Okay, so this is then going to be compressible flow. Okay, so this idea of Reynolds going to infinite in your head, you still should put a limit on there because, well, I could have a very large Reynolds number, but if it's so large that my velocity is much greater than the speed of sound in the medium, well, then the theory changes, right? So then this dies out. So really on the far end of this Reynolds number, far end on this, right, your theory dies out, and then you have to go back to those compressible equations. Right, so keep that in mind. You can't just limit all the way to infinity for the Reynolds number. The structure of the equations completely changes when you do. Okay, what else do I have? And then there's a combination of things that are happening here. All right, and they maybe kind of combine both of these parts of the scale as well. So there's like so this is sort of our range when the Reynolds is going to infinity. And this is just a lot of, and it could either be really simple or really hard at this pass. Right? Because it could be simple if the Reynolds number is big, but we're also in the ideal flow case, and the ideal flow case being here. But then we also see if the Reynolds number is too big, at some point it just crosses this regime when you can't avoid the 3D-ness of the equations, let's say, and all the coordinates mix together, and then all of the stuff I have drops out. But there usually is some level of Reynolds number where I could do this ideal flow or potential flow. But once I pass this some critical Reynolds number that exists, even this wouldn't work because, right, there's essentially so much energy in there that it now you have to put that energy somewhere. It turns into rotational energy. So it can't be 0. So this is this idea that we have these, for any given flow, let's call it C, a critical one. There's just some sort of critical Reynolds number where I trip to turbulence. And that is an issue, and that is the most difficult part about this, just from experiment. So maybe I could maybe break this up, break this world up right here. And then, as long as I'm not actually turbulent flow, I could use this ideal flow. Maybe I shouldn't say ideal. I want you to think mathematically, right? So then this is potential theory. Okay? You remember what that potential thing. And in 2Ds, it's also, right, and then for 2Ds, I am recording right. And then for the 2D case, it's almost solved, right? Because you could just write down any complex potential, get the velocity, and it would work. And that'd be for 2D, right? So this works in like your 2D world. Even 3D potentials work in this world. But once you trip into this Reynolds thing, everything goes out the window. So one thing here, in this, when it's really easy, it's inviscid, and I'm in this world where my solution has that, right? Keep in mind on these sides, right, I don't even need that requirement, right? If it's really slow flow, I can, right, even, flow in a pipe has vorticity in it, right? There's a difference of velocities happening here, so right here, the curl is non-zero, and same can be said for here. Right? There is curl in the boundary layer, but but the ratio of the inertial and viscous terms is so small that I can handle it. So maybe I'll put that here as well. Okay. I'll elevate this one. And there's some, maybe, intersection going on even. Right? You got to think about all these intersections of like sort of parts of the flow. And then when I get to here, which is the turbulent, right? This is turbulence theory. Here is sort of, you have this now problem of it is totally 3D. Right? The flow is completely gone three-dimensional on you, which we have no concept of the solution, what it even looks like, maybe in some extremely simple cases. Right? So this is sort of your biggest issue you have now is you have nothing now. You have a large Reynolds, so now this is going to be nonlinear for sure. And you have this situation now where we're right back to this. Right. Totally. Right. There's a lot of rotation happening in there, certainly. So in all of those non-dimensional things you see, keep that in your head of where the issues are arising. Okay, and we did that calculation, and it kind of sucks, but like we really do live in this world. So we live in a world where it's mostly turbulent because we interact with gases for the most part, so it's certainly going to be turbulent. You know, maybe we're designing things that live in this world, but you know, sometimes we need like microscopes to even see that flow. But the one that we exist in is in this perfectly mix of all world. And it kind of makes sense because, right, all of our length scales are equivalent, so it should be expected to be 3D. And then you have this nonlinear, right? I mean, all of Navier-Stokes is nonlinear theory, but like in the limit of something going to zero, you can make anything linear. So that makes sense about the Stokes flow. Okay, asymptotics can be used for turbulence, but like it doesn't. There's too much that we don't know about like what the solution looks like. So again, what do we have here? This is sort of boundary layer theory exists here, if you remember. Right, and then you could also have that Jeffrey-Hamel. I won't say Jeffrey-Hamel. There is a boundary layer in Jeffrey-Hamel flow, but the theory itself is called boundary layer theory. Boundary layer theory. Okay, and this is Stokes flow. I put that up there. Stokes flow, potential theory, turbulence, compressible flow. I didn't talk about incompressible flow this term, but you know, what's important to realize about compressible flow is when you have compressible flow, the main part about here, so let's maybe sort of go a big old break right in here. So then, right, the idea is in your head, this is all broken up because right here, what do we have? And if you go back, you have to think, to the density field, right? And this side, when you get compressible, now your density field is no longer going to be, right, it won't have a null material derivative. Here it does. So, right, and then past this point, so that's your mind map of fluids so far. And I hope at least maybe the steps of the math are confusing, or you can maybe understand where that's happening. But I hope you have at least the idea of what all this nomenclature means now, at least, from this class. Right? I hope you understand this idea of Reynolds number going small. You can go Stokes flow. I know what the governing equation there looks like. Boundary layer, I know what those governing equations look like. I could look them up. I know what to kind of do with them. Potential theory, right? You could go like, okay, I know to satisfy, I need to have this, and then I know there's this complex thing to do, and that's this idea of a potential flow. So you could look up how to attack your problems with that. So then there's this turbulence and there's compressible flow really left. So I will talk, so then this lecture is I'm going to talk about turbulence for one lecture of what we can sort of know about it. Now I'm not a turbulence expert, so I want to put that out there, right? So all I can do for you maybe is just sort of relay like, what the starting grounds of turbulence, of where one begins, let's say, if you're attempting to handle this. Okay? So turbulence ends up being a highly numerical and a highly experimental theory, which I'm garbage at. Not really, no, numericals I'm really good at, but they just don't spark joy, let's say. And you watch Marie Kondo. Whatever. Okay, so the goal then is then for this, so how do I get a handle then on this solution of Navier-Stokes when it's completely 3D? Right? So that's the idea of it's really tied to experimentation. So by tying to experimentation, right, we can always, right, we can certainly make experiments and measure velocity when we want to. Okay, so then the idea is when you do that and you're past some sort of critical Reynolds number, right? This is this scenario, if this is my velocity and this is time, right? So experimentation-wise, what we see is it could be somewhat from like an internal flow, and I have some sort of probe in there that's measuring velocity. So these are these experiments that you do. And you could even look at velocity profiles by moving this around. Today, I think they use lasers. And then it even would work for boundary layer, right? Because you could have some flow like occurring like here. This is just a mass jumble. But again, I can have, right, again, you have to, right, again, like at this stage, I have no hope of pinning down the theory. So then, right, you then sort of measure the velocity how you want to. Okay, so I think now they use like Doppler laser radar, laser methods to figure out velocity at a point. I think they put things that you put like reflective particles in the fluid, and then you shine lasers to get this velocity. But either way, you come up with some method to figure out what velocity is. It'd be a Pidot tube, which you did with your first one, or you could do electrics. So there's other ways where you put like you can correlate a voltage value to the speed of the fluid there, because it will change the electric properties based on how fast it's moving past your little probe. Either way, you get the classic graph, and I'll do my classic, right? You've seen this maybe multiple times, but let's maybe put it like right here. If I'm at some really slow world, so maybe let's say around here, so let me try to. So there's some maybe like, let's say, litmus, right? There is certainly something going on where after I go up and up and up and I make these measurements, something changes qualitatively. So qualitatively, what's changing? Well, if I'm below there, you're in your laminar flow case, and at steady state conditions. So actually, maybe not do a steady state condition. Maybe let's say we accelerate from a point. It just looks like this. Okay, so then, right, this is this thing where here I have and then here, right, you have this steady. Okay, importantly, that's just what the data looks like when you see this type of flow thing, right? You know you're below this given your parameters, so this right there, right, I'm in a fluid, I have this and this. And you're sort of measuring all these things. And it's at some length scale. So maybe this is your velocity that you're measuring, and then you're in some fluid, and the experiment's happening at some length scale. So it's the plot you have. So that allows you to calculate some Reynolds, some litmus-like Reynolds thing happening here. Okay? But when you get past this, now you have this scenario when, again, you could have non-steady effects. And then it looks like this in a mean sense. In a mean. It's very mean flow. Bad, mad. But it doesn't really look like that. There's this lots and lots of variation. Sometimes it's really big. It looks like it's kind of oscillating. Sometimes maybe just stays on top. Either way, just completely, right? It's almost like quantum mechanics, you could say, where it is completely variation. So this line actually doesn't really exist there, but it only seems it exists in some sort of mean. Okay, so what you really should have drawn is not this graph. Okay, so in reality, right, you just really see this happening in the data, right? So you trip some level of Reynolds number, and then this happens, right? And then you're really, and your sense of an average can almost kind of come from there's some envelope this stuff exists in. Okay, everything we're talking about is qualitative right now. So you kind of see what I'm saying, right? Saying there, and then that mean is really, and that mean is sort of found as like some line existing here. Some best fit line. So in the theory of turbulence, you need to have some sort of mean flow, which we'll call this. And then you also have the instantaneous, right, where you have this fluctuating part about a mean. And that is a U prime. And that is sort of the beginnings, I'd say, of where I would begin. Well, it just looks like if I'm going too fast, this is happening. Okay? Assumptions on this fluctuation in this. I'm going to erase this. I have this, maybe hope you can write this down. Okay, so from experimentation, you're trying to get a handle on this. What happens to the solution of the Navier-Stokes equations when it's really fast, when I can't make any 2D assumptions, etc.? Well, you start with making experiments, and you see certainly this is happening. Okay, so right now it's like, well, what is my average I'm talking about? Are there properties to this fluctuation? All great questions to ask, and that's what people did. People started just making these natural questions. That's right, sort of just interpreting this. I mean, you could certainly, right? If you're an engineer, if I was an engineer back in the day, and I just had this situation, I'd go like, I'll just take the mean and do all my laminar calculations that way. And to some degree, you could do that if you could do that, right? If you want to, right? If you just but you need this experiment is the problem. I don't need my right. If it's laminar and I have these assumptions for Stokes flow, we're at a belief now where I don't need to really even do an experiment. I'm pretty confident in some of those results because I have years of testing on them. But with turbulence, something has to be done about that fluctuation. Because you could just maybe say, you could just sort of maybe treat it like this ideal flow case, or just using the mean flow. But you wouldn't know exactly that fluctuation prior to doing an experiment. Okay, so what happened then? Well, what happened is we are making an assumption on the vector field, right? So this solves, I'm saying this solves Navier-Stokes, right? And this is what I did. I say, you know what? Use this. Use a tilde. I think the solution looks like this. Not that crazy to imagine. Certainly my experiment seems to tell me that, right? Or you're modeling the solution. So it doesn't say it looks like this. You're just modeling what the solution would look like of the Navier-Stokes equations, where this is a mean. I don't need to look, right? So this is, okay, this is the mean flow, and this is the fluctuation. Okay. Now already I've introduced so much extra baggage, right? So the thing is, and what is this, right? So then think about here. What? Right? So we don't know the solution of the Navier-Stokes equations. We can't write out the general solution, right? In heat transfer, you can, right? You can for Stokes flow, but Stokes flow is a limiting case, right? So whatever the true solution is to the Navier-Stokes equations, right, as Reynolds number goes down to 0 in that solution, I should recover Stokes flow, ideally. We think that. There's a lot of questions right, of all this stuff. But that's what's happening, right? So then I have now these things. So what's the mean and what properties of the fluctuations do I have? What's at my disposal? Well, the mean flow is a pretty right, not that hard. Okay, so I'll by a mean, I'll use these bar notations. I'll try to keep, some people use a bar or this bracket. I think in the notes I use the bracket. I might have jumped back and forth. Okay, so I'll try to keep to bracket. Okay, so then I should change this. Okay, so what's important also is it's steady for initial theory, right? So not addressing this stuff. What I'm about to do does not address this, right, time varying part. Okay, and that's sometimes forgotten, I think, right? So importantly, it's not a function of time. I'm only modeling this part of the graph. So I remove the time dependence. I'm saying that the mean flow is steady, no fluctuations happening. But all the time variation is happening in this varying part. Okay, and the assumptions then you want to have on this is it just seems natural there's no bias on the fluctuation. Or is there, right? But a good place to start is to say no bias. What does that mean? That means that that means that the mean that it has a 0 mean. It's just oscillating around 0. So if I consider all of them, right, they're all just equally far away from 0. And what that means you'll see later, right? So no bias, or 0 mean, independently, right? Because this is a vector of fluctuation. What is this? This is a vector. And same with here. This is going to be a vector. OK, so what on earth is the mean I'm picking? It's a pretty simple one, right? It's just going to be for any sort of function, I'll take that. OK, where you have to keep, so this is hard. You have to keep an idea of this. Okay, so the primes are the fluctuation parts, right? The angle bracket is the mean part, and this is the actual component that solves the Navier-Stokes equations, right? So this okay, no prime, actual components on there. So then, right, so a vector of these means would just be component-wise that. Okay, so maybe I could draw that out explicitly, right? So that means that where this is sort of, you see how I'm just writing the exact same. I'm just writing the exact same integral limit part right here. Okay, so really, already let's go over it again. Actually, then, so in reality, because of this limiting or averaging I'm doing, I'm actually saying I'm taking the average of the solution itself, right? So that means your solution model is actually this. Okay. Solution meaning, like, so the solution of the Navier-Stokes equation will look like the mean, right, the time average mean of all the components plus some unknown part. So where before I had 3 unknowns in momentum, keep this in mind now. Now I had 3 unknowns in momentum. Now you have 6 unknowns you'd be looking for. Okay, before the Navier-Stokes equations are modeling the actual u, v, v, and w of your velocity field. This model of the solution is broken up or decomposed it now based on experimental evidence that it really is, okay, whatever the solution is, I can take a mean of it, that's this process, the process of me on my computer saying, give me an average line there. So that's what that's what you're doing on this term right here. You're solving the Navier-Stokes equations, i.e. performing an experiment. You're creating a mean flow. You're saying, computer, tell me the mean of this flow, as Picard would say. And then then you have this also extra unknown thing. The only thing you might be knowing about this is that there's a 0 mean to it. Okay? So that's your starting point. It's where you have to begin, all based from this classic picture. I remember seeing this picture quite a lot in undergrad, so maybe I took some time to really sort of describe it because I was not quite satisfied when someone just said, like, here's turbulent flows. It varies. So that's really this idea, right? So, like, I know it varies, but what does that mean? Well, it means it's like, it's this idea that performing an experiment is really solving the Navier-Stokes equations. So then taking a mean has quite a lot of meaning, actually. Quite a lot of meaning. Okay, so the thing about this mean is a choice I made. I made this choice to say, how am I going to average this? It's the exact same, like it'd be the function you'd call on your experimental plot saying, give me an average. But that's a choice that you would make then after your experiment. So there's room to play in there. But this one's nice, right? This operation is a very nice operation, and we can see why. So this limiting process, I will call this an operator, right? So think of this as, maybe you've never seen this dt before in integrand, but you can imagine how this is an operator, right? All that's waiting for me to do is just to plug a function in here. So this mean has very nice properties that work well, right? What are those properties? I guess if you like to, there's a whole list of them. Here are the ones. Here are the important ones, right? So one is that really for any of these, you just get this. Okay, the mean just ends up being the mean, and that's because of this limiting process. Right, double means is just going to like get you there faster. Right, all that's happening is you're just going right. You're just taking a mean, then taking another mean. So you're just maybe getting closer, but in the limit they would be equal. Okay, another property that's really nice about this. And that's what we say here. Okay, so for all these fluctuating quantities, if it has a 0 mean, then the average. Right, this could be a definition of your fluctuations, that the average of the means are 0. Okay, that makes sense, sort of around. How would you? Right, it's really sort of this idea that if you zoomed in on all the fluctuations, they'd be going up and down and up and down and up and down and up and down. Okay, right, where this is positive, negative, positive, negative, positive, negative, right? So this area. Okay, so, and this is time. Okay, here's, let's say, your averaging quantity. 0 mean means this number is 0, right? So if I integrate this all the way forward, if there's just as much positive area as there is negative area, I'll get a 0 mean. So what does it mean if it's not 0? Well, that means that there's some bias in this. So as I move forward in time more and more, my fluctuations would be growing in some sense. Okay, so sort of. Okay, it's really good to be right here because this would mean that these fluctuations would grow unbounded, right? Would grow right unboundedly if I went to the limit. You focus on, do you recognize that? Or it could even be some constant value. but the idea that there's some bias. So this is this idea of having a bias that, right, if I were to integrate all of my fluctuations over time, it could be either a net positive area or a net negative area, and that would be some amount of bias in there. But for a simple first-run theory, it's good to say that the fluctuations have zero mean. And for experimentalists, it works out pretty well. I don't really, again, not the most expert, but I don't usually see non-zero mean fluctuations. Mathematically, you could maybe do this theory with that. I just didn't quite see it in my distilling of this stuff. Okay, this isn't that hard to show, right? And then another good one. What is it? Oh, what's another? This is an interesting one. This is equal. Right, so if I have the average of the product of an average and a fluctuating part, right, is just the product of those averages. They'd be shown through shown through the algebra. And all this coming from the definition of here. Everything came from. What's the amount of time? Okay, everything's coming from that definition of I pick this type of mean. This mean is really just a linear summation of a bunch of things, so of course it works really, really well and really nicely with everything else. Okay, it'd be hard. I have this little thing where you say we could pick other means, and you could, but your theory would stop there. You wouldn't get that far. The other thing, I don't want to say this. So the other property that's really nice about it is what? Is that it plays well with again, and that's just because I can push things in and out of the integration. But there is certainly some things, right, that this is cautious about something like this. Okay, so this one is coveted of this mean, but it assumes, let's say smooth. It's not really smooth, right? It assumes lots of function, or like I'll say smoothness. If anyone wants to correct me, go for it. Okay, it assumes lots of smoothness, and this dominated and governed a lot of mathematical analysis back in the history of like late 1800s, where analysis was growing up really heavily. And that was this issue of we had calculus, okay, but then physicists started taking these averages of physical equations. They started taking derivatives of these integrals and looking at how those quantities changed because they were trying to get answers. And then a lot of math analysis really went into answering, can I exchange limiting properties? Could I, right, is it really equivalent to take the derivative and then the limit, or the limit or is it equivalent to take the integral, right? So this idea, this swapping of this taking limits, integrating, and derivatives was a huge boom in the late 1800s, I'd say. So this is sort of right, the 1800s math really dominated in that world. It started with people. I don't even care. I think it's just neat, to think like these are very natural questions to ask, where engineers and physicists are taking these equations and doing operations on them, and they're just sort of doing the normal tricks they see in calculus. But then people had to hold on because some things were going wrong. So then mathematicians had to come in and say, well, the problem is that you were commuting these limiting properties, and the functions weren't well behaved. All right, so then let's just apply these things to the Navier-Stokes equations. Right? So it's fair to say that if my experiment said like, okay, did my experiment was all woobly-goobly, that's my solution. But if I take an average of it, I have a nice line. What does that line look like? Okay? So that is this process we're going to do. We're going to say, I did my experiment. Look like this all over the place. And why it looked like this, we can talk about that later, right? A priori, right? So before I had to do experiment, take average, then find out what this line looked like. We want a theory that says, what's this line going to do before me doing an experiment? Can I come up with a theory that can tell me how this line is going to shift about given a flow situation? Okay, so this comes to the idea that, well, just take the averages of our equations. Okay, so then with this is sort of the same thing, right? If I take the average of here, right, just because of the algebraic properties, okay, so that means, so the mean satisfies, right, so the mean conserves mass. But then the other thing you can do is you can sub in your assumption of the solution, right? Okay, this is a vector of all the perturbations. Okay, so then this, right, and then you get here, and now the thing is, this will say, okay, this is going to be 0, right? Right. This lets you also say this. So this is nice. Okay, so we're off to the races at a good start, because what this is saying is that the mean conserves mass. Okay, and then the fluctuations. Conserve mass. Why do the fluctuations conserve mass? It's because of the mean selection we did. Okay, so these things should commute. Do you see? Like, fundamentally, that's what I'm doing right now. This is saying the average, right? The average, right? This is the average, and this is my assumption of what the solution looked like. If you're tying these two things together, you get that the fluctuations conserve mass, which is nice. You would want your fluctuations to conserve mass as well. You wouldn't want to model something and then have any of your fluctuations to be able to create mass. It could be a model that might trick things to work, but that wouldn't make sense, right? So that's an extra credit I would say is dig into this idea of what's really wrong with your fluctuations conserving mass in a limiting sense. But I think this is beautiful already because we're just saying that, like, okay, I got Navier-Stokes equations, and I'll take the average of that. So this process could be summarized, and you do the same thing with the momentum equations, and you do the same thing with the energy equations, right? So, right, this is right. So when you have this is the right. Fundamentally, our theory so far is doing what? Okay, so define and pick yourself a mean that you want to do of how you are assuming things will play out. Okay? Then you've got to also make some assumptions okay, maybe some assumptions on this fluctuation property, informed by some experimental evidence. Okay, so that accumulates to this zero mean property, or no bias. But they've still got to say that, and that has to be said through experimentation. So we already see a very, very interlinked world of experiment theory and experiment, even numerical experiments and analysis. Right? If it doesn't match the theory, it's not going to look good. We observe zero means a lot, and you can really even prove why they'd have to be zero mean. But then we also have a pick this mean. Arbitrary choice I did, but I'm saying, right, it's just the idea of if you gave me your data, never touch the mic, if you gave me your data of a turbulent experiment, right, I could have MATLAB, right, use a different mean. Right, and some people do. But that's the thing, right? So then it is really sort of turbulence theory so far right now is summarized as this. Pick this, do this, and then what you do take the average of the Navier-Stokes equations. This is really called the Reynolds average Navier-Stokes equations. Okay, and what they're doing is this means all the Navier-Stokes equations, continuity, momentum, energy too. So right? Take the average of the Navier-Stokes equations. And then compare that with you substituting your solution form in there. So maybe there's a fourth step, I should say. Step 0. Okay. So then step 0 of turbulence theory really is this pretty weird one, right? Assume the solution form. And that's what we've done. We said the solution of the Navier-Stokes looks like this. That is a lot of baggage in saying that, okay? This is why, right, and if I can get one student to care about the right? This is at the heart of why you could earn $1 million if you did Navier-Stokes equations. Is while numerically we don't see any issues with this theory at all, but there certainly are issues. So the biggest thing is this assumption that, okay, there is a solution, I can do this, is problematic. Certainly it's problematic because this, at least in the theory so far for Reynolds average, has this 1 over t, but there's a limit as time goes to infinity. Uh-oh. Uh-oh. That's tricky to do, right? That's already assuming that any solution of the Navier-Stokes equations, because this is well posed, I could always take the average. Okay? That would mean that I can always do this, it's always valid. There's no singularities that make this term blow up to infinity and throw everything out the window. So that is at the heart of why people are concerned with the full 3D Navier-Stokes equations, is because to solve turbulence, we're doing this process of assuming the solution form. You should be used to the idea of that's the only leeway you get in differential equations. That's the only headway you're going to make, is if you assume a solution form, plug it in there, and derive consequence. So with that in mind, that maybe now there's more, you have more, maybe there, I think one of you already is doing turbulence, right? So then there's this, how do you handle turbulence? Well, there's sort of 3 main methods. Call them methods. Okay, and they're standard ones to date. And then maybe we have a little more language to be able to understand them a little bit more. So they're a little triangle. Yeah, I like the triangle. So there's sort of what I'm doing right now. RANS refers to this limit. Then there is LES methods, and then there is a DNS methods. Okay. So if I have some sort of triangle, so it looks like this. And then what's happening in this triangle is this would be accuracy. Okay, so DNS, and what does DNS mean? DNS means solve the full 3D Navier-Stokes equations in a discretized fashion using a finite element or some numerical method. Make 0 assumptions about the solution form. Just make your grids tiny enough that everything works out. Focus on numerical investigations or be able to quantify your numerical error to it. Take those governing equations from lecture 1 and lecture 2, quit the class, learn numerical analysis, and solve it that way. Have lots and lots of money because you can afford server space that can run computers at that speed. Okay, pay star CCM to do these simulations for you, and you can get really fine accuracy that you kind of believe, because the numerical error didn't blow up. Okay, then there's RANS. RANS makes a simple assumption on this type of a mean right here. And then there's this fancy trickery called LES, or large eddy simulations. So then the other sort of one we can make is this other triangle, what happens. And then here's RANS, and then sort of right in the middle you get this special LES type simulations. Okay, DNS is here. And what is this pyramid? This is money. So money and time. Okay? Money and time is how these simulations go. And these are corresponding, right? So seems like a good bet is this LES simulation. I won't go over LES, but I want you to appreciate that, have you understand, right? RANDS is this idea of here's my average, a time average to infinity with nothing else. LES has a very fancy average it chooses. Okay, so what the LES does is it picks a super fancy average. Okay, the large eddy simulation is an assumption on the average, okay? So what's LES? Won't go into the details of it, but what it is it has, okay, this will look like this. No limits involved at all. Actually, no, it is still a limit. Integrates that time away. How do you do this? You integrate the time away. And then the spatial. Okay, I'm going to do this. I'm going to do this in a vector way. dt. So then I go over the whole region of fluid, and then I go same thing. Yes. Yes. Okay, and what this does, the large MU simulation, so maybe I could put this little LES here. It's a filtering function that's doing the average of it, okay? So it's not really throwing away data like the RAND. It's not just sort of like summing them all up. What it is doing is it's saying I only have a what it's saying is I can only resolve so much of an eddy. Okay, so what I imagine when I do this is like it's essentially related to this. If I want to simulate an eddy, I at least need 4 grids. Right, so this would be your smallest eddy. Right? So the average here is, right, this is what this G function is doing, is that's this idea of size, right? So it's kind of like the Dirac delta things or a Green's function. I know you guys did some Green's functions. Fundamentally, that's the trickery of LES, is it does that for its mean, and it derives, right, other mean average equations. But using this filtering process, it gets a lot more accurate and for a little bit more cost. It's a little more, there's more computational power in doing this because clearly I now have some fancy function, right, where this is okay, and that's your velocity field. So analytically, you start with this. And then you do the same process I had done before, and then you arrive at new numerical schemes that would get you a better solution. Okay, LES is certainly the subject of like a intense computational CFD class, or even theoretically. So if you're a really deep turbulence class, you would probably make that assumptions and go through to get what they are, and then see how making that assumption gives you right, the idea of actually doing this process of plugging in the average and then doing this. So sort of just like I did with continuity, you can do the exact same thing for momentum equations. Okay, so I could take the average of the momentum equations and then compare to a dead marker that should be thrown away. Right, and then you compare that to the momentum equations acting on this. So this is sort of the momentum equations with this inserted in there, and this is the average of the momentum equations, right? And that swapping of that, right? That swapping is important. And what you get when you do this process for the Reynolds average equations is you get at steady state. Okay, also remember here, that so assume, right, I'm saying that the mean is steady for this. Then you get the Reynolds average equations. And what are those? They look like this. I had a U, didn't I? So this is the notational nightmare, because when I write this one out, it looks really bad. But I'll just stick to it. Boom. Oh my God. So this is where the bar notation is actually nice. Bar, viscosity. Boom. And then you essentially get, right, you get an extra term. Like this. I will Is that right? There's no derivative in there. No, that should be right. I think I wrote this down. I did it in symbolic notation. There's one derivative in there, right? No, it's v prime, something like it. Yeah. Yeah. Yes. Okay. So then this is the Reynolds average equation with this extra. Importantly, this extra term arises. This is the most critical thing about a turbulence theory so far of what we have. And this is called a Reynolds stress. Why is it called a Reynolds stress? Well, because I inserted this average in there, I now have some new effective stress that's occurring in the flow. And that stress is proportional to my density now, not some viscosity or internal part. So this stress is involved with inertia somehow, or the turbulent stress occurring in it. And it's a consequent of my assumption that the solution to the Navier-Stokes equations looks like this. Okay? Very big impact of turbulence research is that, at least analytically. Certainly in the mathematical world, it has a big impact. Okay, so a better way to sort of see this momentum equation, because these are all the terms sort of put on out there, is if we kind of do the divergence of the stress tensor like we did before. Keep in mind, everything's incompressible right now. Okay, so without a steady, right? We can even do this not steady state, where I have my material derivative, have an average pressure field, and I have this divergence of a stress field, of the stress tensor. Okay, so right here I have, okay, this is stress tensor. This is the most general equation we had of Navier-Stokes, where before I made assumptions on Newtonian fluids to then break down what this divergence of the stress tensor was. If you remember that, you can go back to lectures 1 and 2 to see how that shakes out. But the important part is, really fundamentally, this is what you have, that you have these normal pressure forces, and then you have these shearing forces caused by deformation of bodies. So you have F equals ma, right? And you have these normal forces and these tangential forces. But for the turbulent case, that T has an extra term, okay? So in the world of turbulence, here's my stress tensor. It has everything I'm used to, and then an extra part. Where brackets are averages happening right now. So this is the stress tensor now. When it was not turbulent, or when some Reynolds number didn't pass some critical value, it looked like this, okay? But now with turbulence, I have this added thing, and there's a minus sign in there. The minus sign because I inserted it right here, and I moved it over here, and this is a square quantity, right? Okay, what is this process of perturbations then, right? Remember that if I have a vector and I have a transpose of a vector, I get a matrix. Okay, so there's 9 components in here. right? Because I have a u, v, w prime, prime, prime. Then I have a u prime, v prime, w prime. Okay? So you see that there, right, and you see that there are these 9, right? You see that there are now 9 components to this stress tensor. So what, right, everything now in the turbulent case of flow for Reynolds, for turbulent case of flow, with my assumption that the solution looks like this, don't really know if it does, experimentally it really does though, right? You get the extra term, which is the Reynolds stress, right? So then what do you have? You have this is, right, Newtonian viscous stress. Okay, Newtonian viscous stress. And then here is this extra term now, where this is going to be a turbulent shear stress. I would really say Newtonian viscous shear stress, turbulent shear stress, right? Importantly, right, the idea is that it's really shears happening right here. They're certainly the most dominant parts, because all of the cross terms right here would be part of this averaged pressure. Well, they don't have to be, right? Now, there are other things you can say, right, on this. Well, right, you could say that is it symmetric? That would give you then 6 components. Certainly this one's symmetric. And that's sort of that's sort of the state. Okay? And this is then certainly then the closure problem we arrive at. Is if I want to model, we start off by saying, how in the heck does my mean flow evolve? It looks like a good quantity to model in fluid flow that's turbulent because I get wiggly lines, but I can take an average after my computer did stuff, right? I can take an average after my experiment and get that data, but I want to know a priori what does that look like if I'm evolving. Well, it turns out because of your assumption on the solution form, this idea that I have a mean plus these fluctuations, you don't know what the fluctuations are either. So you've added more unknowns than there are equations. So this is the closure problem. Okay, the closure problem being just a number of you have more equations than you do unknowns, and it's really embedded in the fact that you made this decomposition, right? So I'll put this arrow going this way. You get a closure problem because of this assumption you're saying. Because of this assumption, right? There's your closure problem right there. And you're going to get it, obviously, because you don't have enough equations, right? You have to make some equation to govern that, or you won't get anywhere, right? Here I have 3 unknowns, and now here I have another 3 unknowns. I don't know the fluctuation in the x, the fluctuation in the y, and the fluctuation in the w, right? So certainly there's a closure problem, right? You introduce 3 more variables. How do you pin these ones down, right? When it wasn't there, when there was no fluctuations, we could close the problem. We could close it by conserving mass, conserving momentum, conserving energy, and an equation of state. We got the 6 equations that we had symbolically, and I showed you how everything's consistent in here. No longer the case because of that friggin' Reynolds stress. Okay, so I need some amount of equations, right? So just like we did, do I need to write that? I mean, it's just this. It's the idea of you're also trying to find u prime, v prime, and w prime, and you don't have equations for it, right? So in your mind, this is just like okay, just like we did for Stokes' assumption, right? Remember the idea of the Newtonian liquid, the Newtonian viscous force? You made these assumptions or constitutive equation where I could relate the strain rate tensor to the stress tensor. And that functional relationship we can work really hard on using like Schur's lemma, which is super cool. And you can then conclude this idea that I can relate, right? This relationship, where I had a stress tensor, but I'm saying I can relate that to the strain tensor by this Newtonian viscous force. So what is one? I need one for this now, too. I need one for turbulence. I need a similar sort of Newtonian assumption of how that turbulent stress relates to the strain rate happening in the flow, of the mean flow. And that's what people did, right? So then you get one of the earliest ones, certainly the simplest ones that we ever had, is the Boussinesq assumption. So this is 1877, right? And this is not the hardest thing to imagine, and that is just this assumption that, okay, I will say that this equals a constant. Right, so the ratio of all of these terms, let's say, because this is a matrix and this is a matrix, so you have to kind of sort of define what that is. So maybe you could, three-dimensionally, you could say, the determinant of this matrix times the inverse of this, etc. But there are ways to assume that, right? I'm just saying that he made the assumption that they're just linearly related. Okay, so a better way to think about this then is just like we did before, right? Boussinesq just said, okay, what in the heck is this? How can I relate this to mean flow strain? And he did just he did just that. He did another Yes. Right? He said that, right? He just said that turbulent shear stress is linearly related to the mean strain rate tensor. Right? So he just did the Newtonian viscous stress assumption again and see how it went. And it worked fairly well, right? It works okay, but I like this assumption that, right, this very old one at least still permeates so much of turbulent theory, because what it says is, at least in this case it ends up working, is that this term ends up looking like this. If I have this true, well, what does it look like? Well, then you get this theory where you remove now your fluctuations, and I can close the problem and just sort of see how that mean flow evolves. And the mean flow evolves differently because the effect of turbulence can be characterized as an added viscosity. Right? It's pretty powerful, and it's one of the simplest models you could have, right? So this term, it has many. I don't think it has many names, right? This even got a name, right? And this is what you'll see is sometimes called the eddy viscosity. Why is it called the eddy viscosity? Well, it's because it has to do with turbulent flow properties. And it should, and I want to maybe say it at the end, right? The idea is like things should be, it's like, what in the heck is going on right here? We're forced to these absurd methods because the solution gets so unruly that we don't know what to do. So you have to do these things where you say, well, there's a fluctuation. Okay, so this eddy viscosity, we're just saying, like, why did I cross a Reynolds number and just all of a sudden everything goes out the window? And it's a property of this three-dimensional stuff, right? Turbulence is a fully 3D theory. You can look at planes in 3D flow and then say something about that, but the fluctuations themselves really are coming from the mixture of all axes. There's so much curl in the idea that there's so much curl you can't quantify in your velocity field now that you're just going to model that mixing up of dimensions as some fluctuating quantity that you don't know, but you can experiment to get at. And that is pretty fundamental to this. So what did I have? I want to see the eddy viscosity. Mixing model. Is there some? I had a. Okay. Almost got a full lecture without embarrassing myself. Did I? Just close your ears. I think I'm actually. God, I was so close, guys. Okay, so there's that sheet. Okay, so then it's called an eddy viscosity because when you have these turbulent flows, right, It's just this wild sort of thing, and there's all these sort of rotating things that like are just, certainly crazy stuff going on, right? So this is certainly what turbulence looks like, okay? And then there's this issue of like what really is a good definition for turbulence, which is also really rough to get around, and people fight about that, like what's a good definition of turbulence, right? So basically we characterize turbulence. Turbulence is certainly something that occurs where I have a large enough Reynolds number that everything goes to shit, right? So that's one definition. Another one is just this idea that the flow is highly rotational and there's the presence of these eddies. Okay, so one way is eddies are present, and eddies present being these seemingly like little pockets of like vortical flow if I look at a two-dimensional plane. Right, so that's one characterized. So the idea of this eddy viscosity then is this is you have this. So another sort of, we modeled this as here, and then I say, okay, I'll divide by the density to get the kinematic, right? It's the scale. Okay, so then the scale thing is I have in these eddies, I'll call this my sort of an eddy length scale. So L, if you took a picture of it, you would see these eddies sort of have this length scale L. Usually it can be fairly large, but it doesn't really matter whatever the length scale is on these eddies. Keep in mind, there's also a length scale here for an eddy. There's a little pocket of vorticity happening, a little pocket of rotation happening here. That'd be L1, which is really tiny. The idea that there is just some characteristic eddy length, right? And then looking for some scale where here's the L, okay, you could have a time scale for the eddy time scale, right? L times a U naught. And then likewise, if I just sort of have this other thing where there's an eddy right here, but there's also a mean flow, right? Or this idea of getting from this point to this point, this sort of time scale would be 1 over strain rate tensor. Okay. I'm sorry, I should have dropped this. Okay, so then there's this, and then this idea that you have, okay, so a VT, the turbulent viscosity, is scales like some constant L, a length, and then the scale being my strain rate tensor. Say U naught. This is some matrix norm, let's say. Did I do that right? I think I'm missing a page on the. Oh man, I'm so close. Where's this length squared? Okay, and then here I substitute in this, yes. Yeah, square length. And this is what's called the mixing length. I added that last minute. I should have just not added it. Okay, so this is called your mixing length. Okay, And importantly for this whole theory, I kind of want to add for this one reason, the idea that this eddy viscosity is a local property. It has to be by the scales. Yeah, I was really just trying to get okay, here's your local of the mean flow. Local being important. I probably should have dropped that. Okay, critically importantly though for this eddy mixing length scale though, is that it's a local property. Because I could have had small other eddy sizes, right? There are certainly smaller eddy length scales than I'm used to. So that this, right, whatever eddy size I'm looking at, right? So if I'm considering very tiny length scales at eddy sizes, well, that means that the strain rate tensor changes locally around that length scale as well. So meaning that this is a local property. So good model, but it's local. So really, you should really think of these eddy viscosities in most circumstances as a function of the space. Anything else to understand here? One other thing is you could see how what happens here now is plug this back in, and you get a fantastic sort of look at maybe what's going on. Okay? And then I plug this back in, and now I have this, and then so then here, and then I get this. So then instead of putting it as a viscosity, I'll use this term. So now I have some constant c. It ends up being around 1. My mixing length scale, and then let's just think of this as squared. That's really what it is, right? Because you have this absolute size to not say, right? The idea is you make this absolute doesn't change the size, but right. So then think of it squared. Okay, and then so what we have so far what we have so for this turbulent mixing length scale, at least for the Reynolds average equations, what you're doing is you're Taylor expanding. You're looking at this function, right? I should have used capital sigma for this. I am so sorry. You guys know it as capital sigma. Fuck. Shit. Okay, so here is capital sigma, where that's the stress tensor that we did. So capital sigma as a function of the strain rate tensor. Okay, I'm sick of drawing the brackets, but just this holds even without the mean, actually, right? So this is the second order term, right? And coming from this mixing length scale model, right? You see that happening where you have the stress, right? So you have the stress tensor, which is a function of strain rate tensor, equal to a linear term plus a quadratic term. Right? So my inputs here, I have this linear term, which is the Newton approximation, right? So I really sort of think of this as sort of Newtonian. Okay, this Newtonian approximation. And not to say that turbulence doesn't involve, turbulence occurs in Newtonian liquids, but this is almost falsely characterized sometimes as like Newtonian liquids are this. I mean, Newtonian liquid is an assumption on this, right? So Newtonian liquids say the first order term has a linear relationship. So that would mean that in a non-Newtonian fluid, your first or zeroth order asymptotic expansion term is no longer, it doesn't have this relationship. Okay? And then our theory of turbulence in eddy viscosities, right, is this sort of This is the mixing length or eddy viscosity. Okay, it's a quadratic addition on here, which varies by a length scale L. Okay, fascinating stuff, I think, on the stress tensors. You get different equations, and then from those equations, you get certainly different things. Okay, so I have another one, and that is now with this eddy size model, what is L? So, okay, the eddy size model works pretty well. I can see that in context that's really my stress tensor with two terms, expansions happening in there. Okay, but then what is L? Okay, and now this L is really, then you go further down in the theory and you start analyzing like flow close to walls or far away from walls, and this is you'll get this inner wall and outer wall or intermediate layers. Okay, so I want to, what do I got left? Okay, so I got a couple pages left, almost. I don't think I'm going to go over, I promised myself I wouldn't go over, I don't think I'm going to go over. I'm not going over today, boys and girls. Okay, so what is L? So L is this idea that we notice that this mixing length scale, if there's a wall present, and I have very turbulent flow, so what does turbulent mean? In this sense, just imagine the flow is so buck wild, I don't have a hope of ever solving it. Also imagine that your flow is completely full dimensional and evolving in the Navier-Stokes equations by those laws. You have no hope of ever knowing what that solution is, but turbulent flow close to a wall is saying that. There is a ton of vorticity lines just shooting off from the walls. Okay, so if this is my wall, you can have these length scales, y, where there are these now regions, and you have an intermediate region now. And maybe you are used to the language now of seeing what these are. It's a mass asymptotic language that we're talking about. We're saying I have some length scale, right? I have some sort of body length scale. Maybe the plate is this long, let's say. It doesn't even have to be the plate. It could just be actually your lens that you've zoomed in on, right? So this could be L. Let's pour L. Script L? Yeah, script L. Okay, so the outer turbulent regime of this flow could be governed by here, and then inner to the wall, there needs to be some length scale. So this is the idea of an inner variable of getting close to the wall. So this one is called y plus, non-dimensionally. So a non-dimensional variable that's close to the wall, what do I reference as? It's called y plus, and then in the outer, I believe we have eta. It changes from other books I've seen. I know that, who says eta? Lumley uses eta. But the y plus is pretty synonymous in all literature, where in your turbulent theory over a wall or some flow close to walls, this y plus is usually referred to as this non-dimensional inner variable. So what is that? Well, what ends up happening is you have, the mixing length model of this type of stress happening in the flow. Again, remember, L now totally characterizes the stress tensor in my flow as a model. Okay, L now, this mixing length is what's characterizing the stress tensor to close my equations. So L in the inner wall, it really kind of looks like y squared, right, for y really small. Okay, so when it's really small, this is kind of characterized like that. What else do we have? And then we have an overlap region where there's some constant kappa. This would be intermediate or overlap. I think overlap is also pretty common. I think Lumley does that one too. And then you have outer. I mean, in reality, actually, there's sort of more of a, let's say, yeah, so then the outer wall is really governed by the length scale of the flow, the length scale of the wall or the flow domain itself, and then some scaling constant as well. But it's constant. There's no y dependence happening in there in your variable. Okay, so then let's just sort of look then at like what's happening for this y. And now let's maybe sort of do an analysis and see, okay, what is going on for this function? You've done this Couette flow, so here's a simple sort of relationship that maybe will explain why you see these logs come up in turbulence all the time. I thought it was the worst. So if you open up a turbulence book, you will see the law of the wall, or the law of the wall, or log functions, or wall functions, or you see logarithms come up though a lot if you're getting close to this wall, this intermediate range. So again, this isn't a turbulence class, but let's sort of maybe get at why those things are arising. Okay, so in this sense, I only have the y. It's the simplest case I can get. So I'm looking then for my mean flow in this x direction as a function of y. Okay, so this is going to be, assume just some educated guessing that you have enough variables, and this is what you're saying. Yes, and then you have up here, outer wall is this u infinity. Okay, so this outer wall with that situation just on boundary layers, it still holds for turbulent flow, where the very far outflow is just this u naught, or at least the scale of that flow is certainly most of it's going at this u infinity or outer velocity. Okay, so then you have another functional relationship that, okay, well, what's this outer one? And that you would assume to be this. Okay, let's see if you can hold with me on this. Rho and then y and delta. Okay, so I have a length scale here, delta. Okay, delta being the turbulent, right, this sort of scale away from the plate. So you know it. There's some length scale where that's going to be true. I won't go into how you actually pin that down. So the process of this term being the theory of turbulent boundary layers, okay, that can get you a handle on there. But then these functions make enough sense. This should not be f, this should be g. So another function g. These functions make sense because you're saying that, okay, this, the mean flow occurring in here, right, if I'm in the inner region, inner? I said inner, right? So if this is inner, the inner is my assumption on this functional form. The inner region will be dominated by viscous forces because I'm close to the wall. That still holds in turbulent flows, right? Don't forget it. And what also still holds is no slip still frickin' holds. Right? Very forgotten about a lot. So you think more about vorticity in turbulence because if you look at above from a plate that has gone turbulent, you'll see oil slicks having all these vertical lines just shooting off. So that's critical, right? So, but the inner wall you still know is going to be governed, right, by viscous forces because no slip still had to obey. So the question is, what's this length scale? Right close to the wall, right? And then far away, you don't have any more, right, viscous forces mattering. So this is saying that it matters that some distance away, I'm just like the viscous boundary layer is now ended. There's some length scale where that doesn't matter anymore, and now viscous forces do not matter anymore. But in the outer, you have turbulent stress. Okay. So before we had viscous stresses happening in the flow in our T, but now with this turbulent regime, we now have a viscous stress mattering. So that is what's happening here. There's still some stress, or this is a stress at the wall. Okay, so now let's non-dimensionalize these equations. They're in functional forms, but it's still possible to non-dimensionalize these, right? What is this? Right? What is this tau W? This is shear at the wall, or shear around the wall. Okay, so maybe put that up here. Okay, shear at the wall is that tau W. Makes sense that, right, whatever it is, you could measure the shear or the friction on that plate. But that's a parameter that would certainly go into characterizing this. Certainly it's a function of y as well. I mean, that's your independent one. But non-dimensionalize, we'll do this. So then the plus variables, you could think of them as now y star. So you're used to saying, right, I always do the star notation, but in turbulence they get rid of the star and they do a plus. So this has a lot of meaning and it means the same thing all the time. So non-dimensionalize this is going to be plus a scale velocity. And this now is the same function, but y velocity over inaccurate viscosity. Okay. And now the question being here, well, well, wait a minute. Well, what was the scale? What's the velocity scale you have? And the velocity scale here is very famous indeed. And it's this. So this is called, what do they call it? This is the wall friction velocity. Okay, wall friction velocity is a very famous velocity scale, and it comes from many arguments. You can get this idea just from the unit analysis of these functions. Okay, I don't quite like Buckingham pi to do these types of things, so you can also understand this velocity scale being, right, it's not the boundary layer, right? Remember, it's not the, just shut up. You know, when you did the speed of diffusion, remember in the vorticity lecture you had this diffusion velocity due to viscous forces. So you had that delta, you did a dt d delta, and you could get something that had a square root in there as well. It's really the same thing happening right here. It's just the idea that this is now the diffusion of momentum. So that's really the clearest sort of scale that you have is, right, the idea that before I was looking at the diffusion diffusion due to viscosity of momentum, okay? And now this scale is the momentum diffusion, but through the forces of through the forces of turbulent stresses. You interpret that how you want, right? So similar, so I'll just say similar. It's very similar to that viscous diffusion velocity. And if you don't remember what I'm talking about, maybe just go back to the notes on that vorticity lecture and see how you can look at that equation and see how viscous forces are diffusing across from a plate. The difference here is you're not focusing anymore on that viscous side. You now look at the with this scale velocity, you're now looking at that other turbulent stress term in your stress tensor. And that's where this comes from. And so there's density in there, so this is the idea that inertia matters quite a bit, and then this fancy shear at the wall is troublesome. You know, what on earth is that? Okay, so that's there, and then we have, we'll have our u infinity, and I'll just use star for here. This is sort of unknown. I mean, this changes a lot. So this is just, all the velocities are scaled by this, right? So I have my u infinity over u naught, and then I minus, this way. And then this would be just like that. So all that's happened so far is I've posed two functions about turbulent flow next to a wall. I've said, what on earth does that mean flow behave like close to the wall? Well, viscosity is going to matter quite a bit, and certainly shear at the wall would matter as well, right? And then there's density in the y. Y's got to matter in both of these. And now for my outer region, I have, well, right, the outer flow is going to be that mean flow plus some term. It can fluctuate as well, right? If I'm above this mean flow and it maybe is going crazy and wild, whatever's around it would also look like that as well. The only difference being I'm far enough away from viscosity that it doesn't matter anymore. All that matters is really that is this turbulent shear stress that's going to move the mean flow around. So that's going to be here. And then density still matters because the mass is resisting motion. So everything's in there. And then you get this beautiful argument of going, okay, where I want these things to meet up, right? Asymptotic matching, right? This property that you have one scale where a variable holds, another rescaled variable where something else holds. You go, I limit them when they get close. They should meet up. And then you get this, okay? So then you'll have the F term. see if I did this right. Okay, so I have these equal. That's right, these equal. Yes, I have an equal. Yes. 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 So this y is now rescaled with the delta, and that's where you have this. All that really happened is I just added 1 in here, but it makes sense because you're saying as this variable blows up, right, as y plus grows. Oh, should I say that too, right? So in these as well, this is this idea that eta, at least what I've seen as eta, is just your y over the large turbulent boundary layer, and then you have a y plus, and that is this, this one. Okay. I've also seen a lot too that, but I don't like the star one. It might be confusing, but I have seen this around where this u naught, the velocity scale, is actually given a special one, and people give it the v star for the friction scale. So you might see v star. It refers to this. It refers to the speed of diffusion due to the turbulent stresses. Okay, so then what happened here is then when this f grows very, very large, right, in the eta variable, they have to meet up. Now, what happened here? Well, what happened here is a multiplication of the inputs in my function f. Okay, so with this y, what happens is I see there's a multiplication of 2 terms that occurs. And what happened is it turned into a addition of terms. So this is I use this example to show you one thing that is almost almost like the no slip condition in mathematics. Is the idea if you have a function, right, where the inputs multiplied turn into the addition of terms, this means, and the other way around, that whatever g is, I have some addition of terms turning into, right, turning into a function with a multiplication of these same terms. So actually, you could even imagine this as, so what's important then is this means must be logarithmic. Logarithmic, maybe. Okay, and again, it's just you have to key into that. And this identification of multiplication of a function turning into additions, it actually is what this idea right here, this influenced information theory, right, by a guy named Claude Shannon. Did the same trick. He said that information is some function about bits, and it obeys some relationship like this, and it obeys it because of it obeys it as just your irrational argument that he made. But then he said, if it obeys this argument, I can invoke the idea that the only function that does this is the logarithm. Any other function's just hiding in disguise behind a logarithm. That's pretty important. Okay, the logarithm is the only function that happens with, right? And if it's not, right, and all other functions are just logarithms in disguise that are doing that functionally. So that's really why you get, right, this logarithm. There are many ways to show it, I think, that work around just this principle. That if I have an inner wall function that has to be related to viscosity, then an outer wall function that shouldn't have viscosity related at all, but then some boundary layer height, and then I have some matching condition, well, that means that it has to be logarithmic. Some people redo this with a differential equation, but they're reaffirming this physical argument, I think, because they know where to go. Okay, so then this is your classic result. This is a kappa, and you get these Law of the walls. Okay, so these are the law of the walls you get from turbulent flow, and it's kind of the only main result I have for you in this lecture is just, through this relationship of shear stresses and turbulent shear stresses, you can at least show this just because of a matching condition. I also like it because it also shows you this whole limiting matching condition, right? This is as L was going to 0, right? So this is the limit as, so this side's, right, the outer flow is the eta going to 0, and the inner flow is y plus going to infinity, and they have to match up. Okay, so then values then that are just sort of known is a lot of experiments have been done for this kappa, and it's really around 1.41 or 0.4. But certainly that 0.1 does end up mattering. And then the other one is this B that's close to the wall one. That one is around 5. So it's about 5. I think which was 0.41? 41 is, the 41's 5 not. Okay. And this is 5.5. So these are these experimental values of what this B should look like. And you have to use experiment. So turbulence is very interlinked with experimental results and always will be. And then A changes. A changes based on the flow. So there's a lot more we can do with turbulence and this theory of this idea that I have the solution of the Navier-Stokes equations. It looks like a mean plus a fluctuating part. And then the fluctuating part is a main quantity of study I have to model somehow. But it really is sort of saying, I want to, sort of the other way around. A lot of people will talk about an energy cascade, which I don't want to do it. I don't think I should do it. I don't think I'm qualified enough on the energy cascade. I mean, the energy, I didn't, I said the energy cascade. Okay, I'll just look. So then the idea is you could have turbulent energy equation. So right, the same thing I did for the momentum equation, I could do the same for the energy. Right? What does that mean? I take the average of it and then compare to what? I compare to the energy equation I have for before for my equations, and then I input into that energy what? I input mean plus fluctuations. And you assume that these are small, so that cubic terms of those certainly fall off. And that's important to do. And there are other ways to do this. Importantly, what happens is you do all of that algebra, and then you get a very large turbulent energy equation. So you end up, getting an equation that is then going to model the dynamics of how turbulent kinetic energy varies. Okay, so then this is this variable q, which is, it's a dot product of the two vectors. So you think it's q squared is really being yes, it's transpose. So that's a fluctuation transpose v, or just the dots of them. Okay, this is a very important, it's a dual. So then this is the mean turbulent kinetic energy. So then a mean of this, track the mean turbulent kinetic energy. And then you get this equation. So there's a capital D, QT. So this is the material derivative of that turbulent kinetic energy, right? So I hope you all know capital D, dt as an operator. Okay, so this is how to model that. How does the turbulent kinetic energy change around in the field? And you get all of these terms. I think I think one of these is wrong, by the way, symbolically, but it doesn't quite matter. I'm not going to test one up, but for interpretation. So it's an equation in terms of fluctuations now. Okay, there's a minus rho, average, turbulent stress, strain, plus a divergence of the average fluctuation. Okay, and then minus an average of a square term. So it's a very large equation, which would make sense because you can just imagine the amount of terms in that energy term is enormous. Just enormous. Okay, so then what we get are then these four terms that then you can now interpret to talk about turbulent energy. And they all have names, and they all sort of come about from just naming them things. So this is the convection or convective diffusion. Okay, a lot of words can be put now. This thing is convective diffusion because you have these fluctuations. You have these fluctuations, right? You have the fluctuation speeds convecting that energy around. This is where that dot is, and then the average of that. Okay, so that's a convective diffusion term. Then you have a production term, as it's called. Production. Then we have work by turbulent stresses, and then we have a turbulent dissipation term. Okay, many terms that are unruly and hard to, if you had no hope of solving the Reynolds, if you had no hope of solving Navier-Stokes equations, by God, you have no hope solving this one. I mean, just look at all the mixture of terms that are happening. But at this stage, I would like it if you could scale this on an exam or something. Right? It's not a lot of terms in there. I get it, right? But you could look at this and you could put scales in there and maybe conclude some cool things. Okay, so then they have this convective diffusion thing. What's that is? That is my fluctuations, right, churning up and moving around, right, fluctuating pressure terms, and then the mean kinetic energy. So the dot product is it moving or convecting an array and diffusing it. The production term is this, right? The production term being this interaction between mean and fluctuations. So this is the mean strain rate tensor, and it's scaled up now by turbulent fluctuations. Okay, I'll say that again, right? So the production term is the multiplication, really, of my mean strain rate tensor, mean, right, scaled up by fluctuation properties. So there's an interaction now, right, or I can produce turbulent, right, or the mean flow, right, you can produce turbulent energy, right, how mean interacts with the fluctuations to produce turbulent kinetic energy. Keep in mind this is local term. Okay, this is work done by shear stresses, and that just comes from work times a distance, okay, so you can get that force. And then you have a turbulent dissipation part. These parts are actually coming from a product rule trick that you would end up doing. It's a dissipation term because it's minus a positive quantity, right? So you have this mu, and then this is the same thing multiplied by itself, so that's a positive quantity, even in however many dimensions you want. So that makes it a dissipation term. Okay. What this is saying is, right, this is saying now the strain rate, right? These are strain rates of the fluctuation field. Right? And fluctuations that are small and closer to small fields will dissipate energy away. Okay? This is the fluctuation term has the tilde, so this is like a strain rate tensor, but for all the fluctuations. So small strain rate and small strain rate dissipate away. They get smaller and smaller. Okay? Work done by turbulent stresses, right, so work done by turbulent stresses, I take the turbulent stress term, and then I integrate over. Production term is the very important one because you have, again, this interaction between, you have the interaction between the fluctuations and the mean. Encourage you maybe to look up the turbulent energy equation and see if you can scale things yourself to see what's going on in it. Everything I'm certainly saying you can just get from just scaling these things and interpreting what they are in a scale sense. Okay, 10 minutes left. So other than that, I can show you a bunch more things, but let's just kind of, I want to end on. I kind of like this picture. What do I want to do? First, let's talk. First, this concept of the 3D-ness of turbulence, right? The 3D-ness being the solution is so three-dimensional that I have to now model the interaction of vorticity and how it adds to more motion in other dimensions by just a fluctuating property I have to estimate somehow with an experiment or numerical experiments. Okay. So that's a big thing. But the idea of it being fully three-dimensional is this sort of, I like to think of these little fountain of energy I can put into flow. So it's sort of a, and there's another one and there's another one actually kind of in between here. Actually, it's actually I think at the very tippy top. Yeah. Whatever, you don't really. So, right, and this is if I have my jug of Reynolds that I'm pouring in, right, the Reynolds number, maybe let's say we're filling it up with air, or we're just pouring energy in really and all. So the top one is Stokes, right? So if it's really low energy, this pot represents, right? This pot represents, if it's really low energy, well, most of it has to be associated to the work done by frictional forces. Okay, really beyond then you can get to these inertial terms right here. This pot is the rho u infinity squared. So this sort of world is governed by, right, really a sort of a boundary layer is kind of intermediately right there. I mean, certainly in boundary layers we do normalize by that rho u infinity, right? But so this idea is now you have this, it's mostly this kinetic or linear kinetic energy. Okay, that's very important, right? And the other thing is in this pot it can handle, right, this can handle ideal cases. Okay, so the more energy I put in there, there's a little intermediate range where I haven't gone fully rotational yet, right, or I haven't fully rotational where everything works. But I have a composition now of nonlinear and irrotational flow, so I can handle it. I can do the ideal flows and I can get places. But more and more, if you keep on doing that, it's got to go somewhere else, and that's a situation, right, where you have to now it goes into it's kinetic energy, but it's sort of rotational. Right, so it went on more and more, and the idea is, right, if I kept on filling it up, it had to go somewhere, and it goes into the field in situations where it certainly is not. There's a lot of rotation happening, and you see that in turbulence flows. You certainly see things whipping and moving around a lot in rotational fashions because there's so much energy got put in there. The frictional work done by friction couldn't balance by work done by friction. It can't balance by just linear kinetic energy itself, so it has to now go into the rotational parts. So that's the key thing, and that's I kind of see it as this way. Why is turbulence hard? Turbulence is hard. Okay, hard for a lot of reasons. I'm not underpinning anything about what turbulent people do. It's amazing, right? Turbulence is hard for numerics and experimental things. But jokingly, I say to myself to remind myself that turbulence is a 3D rotational problem. Turbulence is hard because no one understands rotational problems at all. They're incredibly complex, and like 5 people on the planet understand rotational coordinates and things like that, and they're paid a lot of money. And they work on turbulence. But rotational coordinate systems, etc. It's just really difficult, And that idea of having to capture a completely three-dimensional, very rotational velocity field is just simply too hard. Okay, so I hope you maybe have better descriptions to then read on turbulence papers and maybe just get a sense of what they're saying nomenclature-wise. Go back to that scale on Reynolds that I have that kind of tells you why things are getting hard when you're Reynolds, and this idea, keep in mind this curl or this curl-free vector field assumption is this intermediate part of difficulty. Right? What do you even say for the boundary layer, right? Well, remember I said I had, you said that that the outer flow was curl-free. You said it invested outer layer, so that is this intermediate thing where it's all linear momentum. I can handle that bad boy. But then your turbulence doesn't even let you do that, man. It's all rotational, everything in there. Okay, so then takeaways are things that you just normally are going to get from more analysis on here is one about turbulence is there's more pressure needed for same flow. And this is about 10 times for channels. More pressure is needed to drive one speed of flow in turbulent flow. How can you always remember that statement? Well, like I said, the more you're driving it, or the more you're trying to flow this fluid. Think of it as this cascade of energy. Right? I didn't tell you about cascade. Think about it that way, right? You're driving a lot of energy in there, and then if it's turbulent, a lot of that energy is just going to be wasted into the rotational parts of the flow, not going linearly down the pipe like you want it to. So it makes sense that you're going to have to push, that you're going to need a larger pressure gradient to get what you want in turbulent flows, because you're spewing it away into those damn pesky rotational parts of the flow. One other thing is curvature is sort of turbulent flow is localized. Okay, to walls. And that's the idea that in laminar flow it looks like a quadratic thing, and then for turbulent flow it sort of looks like this in a logarithmic sense. Okay, so it almost looks flat, but there's this region of fluctuation, so it's really, all the curvature is really confined to being close to walls. And that comes from even a general sense of the equations that we derive. You can show that. Okay? Sort of, most. This idea, most energy is held up in these large eddies that are spinning around. Okay, so the larger length scale, the more energy is involved in there. So in turbulence, you hold on to the fact that their energy is held up in spinning these large eddies. And depending on the size of the eddies, it decays down on the amount of energy you have. This is really this energy cascade we say, right, where if I have log energy, and then this awful unit called a wave number that I fucking despise, because it's a wave number. A wave number is 1 over a length because you put it into a sine function, so it's wholly unreasonably hard to interpret. Okay, this is the idea that for energies, if you look at just the size of these eddies rotating on a length scale basis, so K here, 1 over large eddies, certainly smaller, over 1 over small eddies. Okay, so a wave number being, say I have some domain here, I'll call it L1, then a big eddy here, capital L. If I think of a wave being like the smallest mode of a wave that could go through here, okay, you could think of it as like really, it's a Fourier decomposition, right? The wave number would be kx, right? And because I need a 1 over x variable. So where this k is your length scale of your computational grid, or your unit of size. So in a wave number sense, you have to be 1 over length, and that length is identically the actual size of the eddy that's rotating. So the energy cascade's saying, well, these energies, right, the energy is mostly going to be held up in that large rotating eddy. And as I go smaller and smaller in eddy length scales, there's a 1-to-1 correspondence of how much energy is associated to that eddy. A lot to digest. The idea is you have this plot in mind. And the most weirdest thing is that it's almost -2. So turbulence has a fundamental thing where it's almost even numbers, it seems like, all the time. So that's the wave number, that's, they say, E. I'll just say just proportional to K, where K is a wave number. Okay, but that's incredibly hard to, I can never, I hate. Okay, the other thing is, like, really, another big thing is we're assuming big part of it, F. Okay, turbulence right, arises as really an extra viscosity term, and that's that mu t argument that we have. What else do we have? Okay, then I had G and F there. Really you're saying sort of the same thing, and that is that you always are tied to some amount of experiment, whether it's numerical or real experiment. It certainly has to be really done, though. Okay? And that makes sense because so turbulence is bound to always do experiments, and it's bound to do that because you have to characterize that fluctuation term, or the Reynolds stress of some way. Okay, the turbulence is governed by a DNS. You just solve the Navier-Stokes equations and just have a ton of money, or this Reynolds average equation, which has a larger scheme, large eddy simulation. The large eddy simulation obeys this, right? So large eddy simulations, they have a filter on them that ignore tiny eddies. So a large eddy simulation, what it does is it tries to find all the energy in your flow, and only kind of does this about 80%. Where here, ignores small eddies, usually about 80%. Okay, so if on a large LES simulation, it does this trickery where it has grid sizes locally that only can do so large of an eddy size, and it has a filter function on that average, and numerical analysis gets you here, and then you really shoot for this 80%. And there are models for, implementing the Reynolds average equations. There's K epsilon models. There are models that essentially look at those average equations and come up with more equations to solve them. Okay, so closure problems. So then turbulence, right? It's always will need experiment or mind for more equations. You need that. So you're linked to it. And right, the idea is think of in turbulence, right? What is your experiment doing in turbulence? Your experiment is solving the Navier-Stokes equations. We think. Okay, so you set up an experiment, you have it evolve through time, and we assume that what's happening is nature herself is evolving the Navier-Stokes equations forward in time. You grab that data, and then you work again. And the mind is used in turbulence, right, to come up with models for that solutional form. So you use your brain to come up with, what do I think the Reynolds stresses are looking like? What are some correlated type things? The eddy mixing length scale is a fairly good one, but there are many out there. And why are there so many? There are so many because we'll never know the actual solution to the Navier-Stokes equation. So what we're left with is trying to just come up with what it looks like on our own. We don't know that the model of Navier-Stokes equations truly is the right one. If it was, because we never observed flow to blow up into infinity, right? So hopefully Navier-Stokes equations really do satisfy that. But we want solutions, so what do? We assume it's the mean plus a fluctuation. That's what every experiment's ever told me, so I'm going to run with that and get some numbers. So that is my overview of turbulence in one lecture. It's pretty fun, I hope. Maybe you have a better skill set or tool belt to understand what these turbulence people really are talking about. If you seek to go into it, you're really going to look into better. If you want to do turbulence or research, I would say you're going to really work on that LES stuff for numerics. Okay, bye.